And we are recording. Okay, so, hey, eyes up here. So anyway, what we have been looking at is integration by parts. Pay attention. I'm over here, not over there. Okay, anyway, so what we've been looking at up until now is integration by parts. That is integration by turning something into a more useful or into a simpler formula and taking the integral of that. So, how did the integration by parts formula go again?
The integral of u dv equals uv minus the integral of v du.
The integral of u dv equals uv minus the integral of v du, right?
Voodoo.
Okay, so let's go ahead and do a quick example. And I'm going to show you some of the other really interesting and powerful things that we can do with integration by parts. Now, the simplest use for integration by parts is if we're doing something like taking the integral of x sine x dx. So, what's u?
X.
And what's dv?
Sine x dx.
Sine x dx. Okay, so what do we need to find?
du.
du,
dx.
which is dx, yeah. And we also need to find v, which is what?
Negative cosine of x.
Negative cosine of x. Yeah, don't worry about the plus c until you're done taking the entire integral. Just tack it on at the very end when you're done with the rest of the problem. Why? Because the arbitrary it's an arbitrary constant that's being added on, and whenever we're multiplying it by, it doesn't really matter what we do with the arbitrary constant. We're always just going to be taking it out of the integral, adding it on the end. So it's just going to be a whole bunch of arbitrary constants added together, and when you add together two arbitrary constants, it's still an arbitrary constant. So it's easier just to not worry about it until the end. So anyway, now we plug this in to the integration by parts formula. What's u?
X.
And what's v? Negative cosine of x minus the integral of what's v?
Negative cosine of x.
Negative cosine of x, and what's du? dx. Grand. Okay, so now let's actually compute the integral. Can I simplify this in any way?
Plus.
Yeah, we can pull out this, or we can pull out that negative sign, so it's plus. And what is the integral of cosine?
Sine.
Plus sine. Plus c. There's the plus c. Okay, fair enough?
Mm-hmm.
Yeah, this isn't too hard. Now let's try something a little more interesting. Now I said that integration by parts is really useful when one of the components that we're taking the product of, when we take the derivative of it, that makes it simpler. Okay, so if one of the things here becomes simpler when we take the derivative, then that's a good sign to use integration by parts. Because, when we take the derivative of x, it disappears. But when we take the derivative of sine, it just changes shape. It doesn't get any more or less complex. But we can also use integration by parts in situations where neither side gets simpler when we integrate or when we derive. And this is called solving for an unknown integral, and that is today's subject. So everybody needs to have paper and pencil on their desks, and everybody needs to be ready to take notes. So, do you guys think this is too warm or too cold in here?
Why would it warm?
Or is it perfect?
It's good.
It's good? It's too warm for me. Solving for an unknown integral. Now, we don't have any, we're above the Arizona standards, so we're not going to post that, but our objective is to use integration by parts to integrate to integrate difficult products. Okay. So, y'all ready? Let's get started. Okay, so what if we need to take the integral of e to the x times cosine of x dx? What is this? So if I take the derivative of e to the x, what will I get?
E to the x.
If I take the derivative of cosine, what will I get?
Negative sign.
Negative sign. So will either of these get simpler as we go?
No.
Will either of these disappear if we take enough derivatives?
No.
No. But there is a way that we can use integration by parts to solve it anyway. Using, of all things, algebra. Okay. So, we still can write this in the form of integration by parts, right? There's nothing stopping us from writing it out into the formula. We're just not certain if it's going to be useful yet, right?
Yeah.
So, let me see, I'll just rewrite down the formula because I'm a total nerd and erased it. How did it go again? It was UdV.
U equals UV minus integral of VDU.
ddu. Okay. So if we write it into this, well, what would our u be? Yeah, it could be e to the x, and what would our dv be? Cosine x dx. So there's no reason why we couldn't make our u be cosine of x and our dv be e to the x dx. We can change the order all we want. But we might as well try this. Okay. Now, let's go ahead and write this, or that. What do we need to find?
DU.
du, and what?
V.
du equal ex dx.
So du is e to the x dx, that's true. And what's v?
Negative cosine x.
Check that.
What?
Sine
Sine.
x.
Sine of
Sin
x.
x, yeah, this goes.
Okay. Plus e.
Yes.
Wait, you said.
Is it necessary?
You said. Wait.
Huh?
Negative sine of x?
No, it's cosine. It's sine of it.
It's just sine.
Sine.
Because
Oh,
I
you're
first
right,
said
of
negative-
course.
Okay.
My bad. You're right. You're right. My mistake. Okay, so now let's go ahead and plug these into this guy here. So what's u?
EX.
E to the x
Sine of x.
times sine of x minus the integral of
Sine of x. Yes, yes.
minus the integral of sine of x. U is e to the x dx. Huh. So this is kind of interesting because when we rewrote it in integration by parts, we got back an integral that looks an awful lot like the one we started with. So, that's very interesting. Do you think if we take the integral of that again, do you think we might get back what we started with?
Yes.
I think that makes a lot of sense to me.
Yes.
Let's try applying integration by parts again. Okay? Let's just do the exact same thing. So, what would u equal over here?
EX.
Huh?
EX.
Yeah, e to the x. What would du be?
EX. EX.
What's dv?
Sine of x dx.
Okay. And Isaiah, what's v?
Negative cosine x.
Negative cosine x. Okay. So now I'm just going to rewrite it again. I'm going to go ahead. Do you guys have this stuff here? Okay, yeah, I'm going to erase this. Just going to wiggle my camera, make sure it's grand. Okay. So now let's go ahead and rewrite it again. So now we have e to the x sine x minus, okay, so what's u? Or let's say
X
e to the x, what are we going to multiply that by?
negative cosine of x.
Yes, that's e to the x times a negative cosine of x. Okay, then minus the integral of what's v?
Negative cosine of x.
Negative cosine of x. And what's du?
Dx dx.
Ex dx. So now let's go ahead and let's go ahead and just distribute some of this stuff, simplify it a bit. I distribute this negative sign, what happens to these guys?
Comes positive.
Okay, so that becomes positive. I'll go ahead and pull this out, and that becomes negative. But I go to distribute again, or it becomes positive. I go to distribute again, it becomes negative. Yeah. Okay. Negative signs, man. And all of this is equal to the integral of e to the x cosine dx. Okay, so are we in agreement? Does this make sense?
So we don't think you're going to
Hmm?
go with that.
So we rewrote this into the integration by parts formula. Then we rewrote the integral that's here into another integration by parts formula. Do you suppose we can keep going?
Yeah.
Why couldn't we keep going?
Same thing as
Well, it's the same thing as we got at the beginning, but is there any reason why we couldn't stick this into the formula again?
No.
There's no reason why we couldn't. We could keep going forever. Would that help us?
No.
That doesn't sound very useful to me. But check this out. This is over here. What would happen if I add the integral of cosine of x e to the x dx to both sides, just using algebra?
You would get
Get rid of one.
2. Oh, wait.
No, this should be cosine of x.
Yeah, so.
Dx.
2.
2 integral
Integral.
dx.
Cosine of x.
Exactly. So now, 2 integral e to the x cosine of x dx. And what happens to these two?
Cancel.
They cancel out. Poof, poof. So now we have 2 times the integral e to the x cosine of x dx equals e to the x sine x plus e to the x cosine x. Let's divide both sides by 2. These 2's, what happens to these 2's? They cancel. Okay, great. So how does that help us? Well, we just kind of stumbled our way into the answer. We were wanting to find the integral of e to the x of cosine of x dx. And we found it. There's just one tiny little thing missing. Eli, what is it? There's one tiny thing missing.
Plus C.
Plus c. Ah. So, we didn't actually really take any integrals here, but we still kind of managed to stumble our way into the answer. Okay. Who's a little bit confused about how we got here? Nobody? Great. So what does this tell us? How can we how can we bottom line this? In other words, what was it that is special about this equation or about this integral that makes it so that we can solve it using this method?
Doesn't really care about x.
Well,
They're both in a cycle. And you're trying to see what it is.
no, they're both cycling. They're both integrating them or deriving them will both get us back where we started with, right? Cosine of x will eventually get us back to cosine of x if we take it enough times. E to the x, integrating it, just gets us back in e to the x. Same for the derivatives. So, because of this method, so we can kind of make a blanket statement. That this marker is empty. Close enough. So we can make a blanket statement that if our integral is a product of two functions that can give back themselves after differentiation. We can find the answer.
Spell differentiation wrong.
Differentiation. Yes, I did. We can find the answer by solving for an unknown integral. Oh, there we go. Okay. Now, let's see if we can come up with another one. So we'll need functions that can go back to themselves. Now, e to the x does that, cosine and sine do that. There is another I can think of. Cosh and sinh. Okay, so let's go ahead and try one with cosh and sinh. Not everyone was here when we talked about cosh and sinh. They're called the hyperbolic sine and hyperbolic cosine functions. You don't need to actually worry about what they are. They're used in some really freaky advanced mathematics. I've only needed to use them myself a handful of times. An actual application for hyperbolic cosine and hyperbolic sine. It's used in finding the curve made by hanging ropes. Like if you have a cliff and you're hanging a rope off of it, hyperbolic cosine and hyperbolic sine can give you that curve. It's weird, I know. It's not something that you're going to need to worry about at all in high school. Maybe in college. Maybe.
In what field of like major?
Physics, engineering. Okay. So anyway, let's go ahead and say that we have, I don't know, let's say,
What's the most complicated engineering?
most complicated engineering? That's a question without an answer, and it is off topic. Okay,
Petroleum.
so let's say I'm taking the integral of hyperbolic cosine, also known as cosh, of x times, let's say, e to the x, and I go ahead and say give that a 3 and a constant multiple.
I got a
There.
question. Did we write this down? That's the one would be useful in college.
You know what? Art isn't particularly useful in college, but are you never going to look at art? Music isn't particularly useful in college. Are you never going to listen to music?
It is useful.
Music is a very important.
Math and science are no different. Some people use it. Not everyone does, but everyone should learn it. Okay. Or did I just blow your mind? Okay, anyway, so as a review, for those of you who weren't here when we talked about cosh and sinh.
They go back to each other.
Yeah. Hyperbolic cosine and hyperbolic sine just bounce between each other.
Is that a hyperbolic tangent?
There is.
What's that called?
It's just a hyperbolic tangent.
How about cosecant?
Cosh.
So it also exists for the others as well, but I don't know anything about them. In all my life, I've only ever worked with cosh and sinh.
And
Okay. So the derivative of cosh, hyperbolic cosine, is equal to hyperbolic sine, and vice versa,
Why do you call it sin?
because that is obviously cosh, and sinh just rolls off the tongue nicely.
Sin.
Really, I mean that's all it is. It sounds nice.
Shin.
And the derivative of sinh is equal to cosh. Okay, so what's the integral of sinh?
Kosh.
And what's the integral of cosh?
Sin.
So if we keep taking the derivative or keep taking the integral, they'll just bounce back and forth. Yeah?
Yes.
Kind of like how cosine and sine they kind of bounce back and forth but get a negative sign each time. Something that it has in common with imaginary numbers, but that's for a different day. Okay. So let's go ahead and write this using into the integration by parts formula. What should we make u?
Cosh of x. EX.
Doesn't really matter, honestly.
Yeah.
But which one?
Yeah.
EX? Okay, that's a 3, yeah. So you're thinking we should pull out the 3?
Yes.
That's a good idea. We can pull out the 3 now, so that way we don't have to worry about it later. So it's a constant multiple, so we just pull it out. So we're saying u is e to the x. Okay. Now what about dv? What's that?
EX.
Kosh X.
Cosh x dx.
Oh.
This would actually work if we switch these around too, but you can try that yourself if you want to. Okay, great. Then what's du?
EX.
So EX dx.
Ex dx, and what's v?
Sin X dx plus C.
Sin.
Sinh of x. No plus c yet. You're breaking my heart, Eli. Every time you put a plus c before the last step,
But you always,
somewhere a mathematician dies.
but you always say the dx always turns into the arbitrary constant.
It does. At the last step. Don't worry about it until then. You're right. It actually is there. We're actually just ignoring it until the last step because it isn't important until then.
Will some professors fight you at T?
Oh, 100% of professors will dock you for getting to your plus C at the end.
No, he means
No, I'm
right
going to
there.
add it right now. Like,
Oh, if you add it right now? I would just avoid adding it right now. Yes, mathematically it's correct. It is there. But, and they probably wouldn't knock off points, but the thing is that could get confusing. Now you're having this constant wandering around that might that might be messing you up. So you really shouldn't put it there. That's really what it comes down to.
Can't you just? Okay,
Did you see what I'm saying?
I do see what you're saying, but like the last thing you said, like anything multiplied by an arbitrary constant is an arbitrary constant.
Yeah.
So I think we'll just turn back to the same.
Yeah.
Yeah.
The point is that it doesn't affect, is that the arbitrary constant here doesn't affect anything really ever until the last step. So we just ignore it and put it on at the very end. If you look in like even solution manuals for this book, they don't bother adding it until the last step. So just don't put it in there yet. Wait until until the very, very end. Just think of it as being I'm done with this problem. Now I'm going to put a plus C on it. Okay, anyway, let's go ahead and continue. So, okay. So, what's U?
Dx.
E to the x. And what's V? Ah, lame. That's right, we have short classes today.
Minus the integral.
Okay, go ahead and finish this problem. You can go ahead and finish this problem as homework.
Sub x dx.
But we don't know how to do it.
Yeah, you do. We just did it. We just did another one.
This is homework.
Yeah, go ahead. Finish this homework. We'll go over it on Monday.
Can it be extra credit, please?
Yeah, sure.
Monday?
We'll go over it on Monday.
Do you remember anything?
Of course I do.
Will we be back by
Did we
Monday?
never give anything back?
Probably not. No, we'll be gone. No, we'll be gone all day.
You guys will be gone on Monday?
Yep. All star.
All Star. Okay, and go ahead and say bye to the nice person watching this.
Bye.
Oh, that doesn't matter.
Okay then, and that is